Hello, my name is Danny Nolan and I'm the Director of ChassisSim Technologies. And welcome to this latest ChassisSim video tutorial. And today, ladies and gentlemen, we are going to be talking about the ChassisSim EV Powertrain toolbox. Now, for those novice ChassisSim EV Powertrain users, my apologies for this. This is a video that has been long overdue. So, let's get started. Okay, here's the thing about EVs. EVs really have this reputation of either being it's all way too hard and it's all either voodoo science slash rocket science, or particularly in a lot of motorsport corners, they're viewed as the work of Beelzebub himself. But here's the problem. The problem we're dealing with is the fundamentals of EVs aren't particularly well understood, which is why, in order to understand the ChassisSim EV Powertrain toolbox, I'm going to have to go through a little bit of revision in terms of what I've done with some of my earlier tutorials. So I'm going to show you the fundamentals of EVs. I'm going to go through some really basic hand calcs so we know what we're talking about. And then we're going to talk about the ChassisSim implementation of EVs. So, why should you be paying attention to this tutorial? Now, what I'm showing you here is some motorsport EV correlation. Now, quick disclaimer here. ChassisSim has been used in a multitude of EV powertrain applications. Unfortunately, I have to be very circumspect about what they are because we are signed up to NDAs up to the wazoo. That means if we start talking out of school, we can be taken to the cleaners. And given the amount of importance that's been placed on EVs in the motorsport, both in the motorsport community and in the OEM community, you got to take the rough with the smooth. That being said, what we've got here is we've got actual is coloured, simulated is black. So the speed correlation, members of the ChassisSim community in terms of speed, steer, throttle, longitudinal, lateral G, this is something that you're all used to. However, the real things to pay attention to are down here: the voltage pack, charge power, current pack. And as we can see, ladies and gentlemen, apart from the initial brake applications, we've pretty much got it nailed everywhere. And the only reason that we didn't nail it initially is that was an earlier version of the EV Powertrain toolbox that didn't have paddle regen incorporated into it. But bottom line, the nail here is that what we're going to discuss today, ladies and gentlemen, is not theory. What we are discussing today, ladies and gentlemen, is something that has been applied in the real world. So this is not theory, this is practice. Okay, in order to understand electric vehicles, we need to go through a bit of a revision about their basics. So basically, any EV powertrain out there can be represented by a battery pack and a motor. So basically, it's a simple voltage resistance circuit. Now, mathematically, you are using voltage is equal to I times R, power is equal to V times R. For your younger engineers out there, commit this to memory. It's really, really, really simple because on a macro level, you can actually get an awful way down the road in terms of what you need out of an EV powertrain by using these two very simple equations. So let me illustrate to you with that in an example. So let's just say that I've got an EV powertrain on a free cell lithium power back drawing about 30 amps. So typically we've got a working voltage of about 10 volts for that battery pack. The current is 30, so we're dealing with about a third of an ohm in terms of resistance. So your power is about 300 watts, and that's typical for that free cell application. So what's going to happen if we go to 4S? So going to 4S, P is equal to V squared on R, which is 14 squared on 0.33, which is 593.9 watts. And the current is going to be 14 volts divided by 0.33, so that's about 42.4 amps. What I have just described, ladies and gentlemen, is the ability of when we take something like this and we jump from 3 cells to 4 cells. And this really illustrates, ladies and gentlemen, a very, very fundamental point here. Do not underestimate what you can learn from the electric RC car and aircraft communities, particularly when you race RC electric cars and when you get into high performance fixed wing aerobatic, fixed wing high speed, and acrobatic heli. And also, I would also say for that, drone racing as well. You will learn a truckload about what a lithium polymer pack looks like, how to size it, what happened, and more importantly, what happens when you get things wrong. I mean, a lot of when Formula E first started, and some of my initial launch customers walked in and said to me, "Wow, you must have a double degree in electrical and aerospace engineering." I said, "No, I don't. I've just been killing myself on this for the last 20 years. And besides, by the time you fried the amount of electric motors I have, fried the amount of ESCs, battery packs, and my finger went through the prop of a radio control plane, you walk around like you own the joint." And that is the domain knowledge that you get from that. And for those of you who are EV novices, I would strongly recommend getting into that. Not only is it a lot of fun, you're going to learn an awful lot along the way. Okay, first things first, before we talk about how we entered this into ChassisSim, we need to discuss about what is about the two aspects of an EV powertrain, and that is the lithium polymer, lithium ion pack, and the electric motor. Now, the lithium polymer pack, basically, it's for, the soul of this is the voltage versus cell discharge curve. So sometimes you'll see this cell discharge curve expressed in kilowatt hours. Look, that's a fair way of doing it, but I actually like to think of it more as capacity in terms of milliampere hours. Here's why. If we take a look at this curve here, you'll see this color coding here. We've got 1C, 10C, 20C, 22, 25C. You can see how the performance of this battery pack pretty much starts to fall away once we load up the battery cell. Now, what we mean by 1C, 10C, 20C is that's a multiplier of the current that you're running through the pack. So if you've got a 4 ampere hour pack, if you're running at 1C, you're drawing 4 amps. If you're running at 10C, you're drawing out 40. If you're drawing out at 20, you're drawing 80 amps and so forth. But what you want to do, the holy grail here, is that you want this as flat as possible. Now, arranging these cells into a pack, here's the language of how you specify a battery pack. So typically, it comes down to the number of series S, number of parallel P. So the voltage of that pack is the number of series, voltage of the cell, ampere hour of the pack, number of cells in parallel times the ampere hour of the cell. You will live and die by that. And for those of you watching this, I would strongly encourage you at this point in the video tutorial to pause this and write this down. It's very, very important. Now, the next point with electric propulsion is the motor. Now, the thing about what separates an electric motor from an internal combustion motor is the fact that pretty much the torque curve at full throttle is flat, and it only starts to drop off as the voltage starts to drop off. So this is one of the key reasons that you've got sort of a factory Tesla-free Tesla S that can more than hold its own when it drag races a muscle car. And typically the nice thing about this is that the torque the power curve stays fundamentally flat. Now, in an earlier tutorial, I talked about how you relate this power curve to an internal combustion engine analog, so you can use that to specify what you want out of an electric powertrain. And I would strongly advise you to look at. The other thing too is, as we all know, with an internal combustion motor, the fuel, and particularly when for a performance motor, your fuel and your motor are fundamentally linked. Multiply that by a factor of 2 or 3 for an electric propulsion system. Your lithium polymer pack and your motor are fundamentally linked. You cannot have one without the other. It's as simple. It is as simple as that. Now, in terms of what you're going to enter into ChassisSim, and I'm going to walk you through the mechanics of this shortly, is number one, you need a cell discharge map. That's your fundamental. Get this right, everything will fall. Everything else will fall into place. Now, everything else will fall into place. Also, too, this little curve that I've got here is a very, very, very simple lithium polymer, lithium ion cell discharge pack. Is this the perfect? Is this the perfect cell discharge curve? No, but it's enough to get you going. You then specify the number of series and parallel, but we'll get to that shortly. Okay, the next thing is the engine. This is the 3D map of those flat torque curves we were looking at. So as you'll see, as the voltage goes up, the amount of torque that you can sustain keeps on going. Where the voltage drops lower, that drops off. Now, we'll talk about the mechanics of how to do that shortly. Also, too, the other thing that we're going to be making extensive use of is the variable throttle maps, whether this is for a motorsport EV application or a road car application. So what we typically have, first column will be track distance, second column is throttle as a percentage. And ChassisSim will use that, whether it's an EV powertrain where you're deciding to figure out how to back off to try and save energy for a stint, or whether it's for a road car application, these numbers are a lot lower, where you're trying to see, okay, for a typical highway cycle, how much ampere hours are you going to use so that you can size to the pack to an appropriate range. The other thing too is specifying the Regen torque map. We're going to talk more about the specifics of this shortly, but you could also specify this as brake pressure versus brake torque, and you've got the option to specify that at the wheel or at the flywheel. Totally up to you. Now, let's talk about how you enter this into ChassisSim. So what I've done here is I've got the ChassisSim version 3.40 beta here, and because the release of this is imminent, I figure it makes a hell of a lot more sense to talk about this as opposed to the previous versions of ChassisSim. So to get that, we either click on the engine graphic or click on the engine on the toolbox. Now, a couple of things here. First things first is the red line is specified in exactly the same location, whether it be an internal combustion motor or whether it be an electric motor. So that's specified right here. And that's actually a bit of a trap for young players. So to click up to set up the electric powertrain, we click on here and we click here to enable the electric powertrain. So first thing first, we click on the cell discharge table, and this is our cell discharge map. Now here I've been a little bit cheeky and I've specified a high voltage lithium polymer cell. But again, this is an example of a really, really very simple but very effective baseline voltage map that you can use. So here I've just specified 4.3 going out to 3 volts. Now, the axis of this is the cell the axis here is your cell capacity in ampere hours and how much current you're drawing. Again, this is the soul of your battery pack, and in a perfect world, you want that to be as flat as possible. Now, here you specify the number of cells in series and the number of cells in parallel. The number of cells in series is dictated by the amount of power that you want. So typically, you take your working voltage, which typically will go between about 3.5 to 3.8 volts per cell, depending on how good your battery pack is, and you simply divide that by looking at your electric engine power curve and figuring out how much power you're going to need. So that dictates the number of cells in series. The number of cells in parallel pretty much is dictated by how much range you're going to need out of the vehicle. You specify your cell capacity, and and this is your initial state of charge. So here I've got 100%. Now, here are the cell thermal properties. I'm not going to get into this just now, but this is your ability to control. Your ability to control how the battery pack will heat up and cool off as it runs over the lap. Is this perfect? No, but as a good rough rule of thumb, it puts you in the ballpark, so you can start getting a feel of what your cooling system needs to do. Now, in terms of your engine torque properties, your fundamental basic engine torque properties are specified here. Click here for your engine torque properties. And again, this is a very, very basic engine torque map. The horizontal scale here is voltage. This is RPM. Now, this is specified on a REMI HVH motor, as we saw in the initial presentation. But that allows you to dial that in very, very quickly. You also have the option to current limit this as the pack temperature goes up. Also too, and here's something that's really, really important, you've got your multiple torque map options. Now, the thing about electric motors is because they have so much torque, you really need to have the ability to be able to regulate torque as a function of to regulate torque as a function of both RPM and throttle. And this is where this comes in. So typically you'll click on enable engine torque and multiple engine torque maps. And in here, you'll specify the number of torque maps that you can use. Let's say that's 4, and I'll specify 1 as the current torque map. And here, we can click on Edit Engine Torque Map 1. I'll click up my access properties per cell. That's set to 10,000. I'll click on OK. And here, I'm just going to set up a very, very simple linear response map, say set at about 350 Newton meters of torque. And I'm doing this by clicking on the control, using the arrow keys. I'm going to use the Shift key, and I'm just going to do a quick linearize. So that by using the L key. Now that is a very, very simple but very effective linear throttle curve, and particularly for your road car, for your high-performance road car motorsport applications, you'll be playing with that quite a bit to try and regulate the amount of torque that your drivers are actually going to be comfortable with. So that's something that's a really good thing. Also too, you've got the option of being able to vary this as a function of track distance. So if you've got your engine torque map selection on the steering wheel, you can dial that in. You've even got the whole push to pass thing where you can specify a base torque map that you want to use for push to pass and how long you want it, how long you want this engaged for. Now, the other thing too is that you can also run multiple laps with this. Now, the reason you would want to run multiple laps is that you want to see for a particular stint how the voltage is going to sag over, how the voltage is going to sag over a run, so that you can see how you need to vary your throttle versus distance maps if you need to conserve energy. That's where the import throttle versus distance map comes in, whether it be for both a road car application or a motorsport application. Now, in terms of your charging regen options, you can go really simple, where you just simply specify a max charge rate and a charge efficiency. And you click here to enable the regen effects on braking. You will also have the option where you can click on here, where you can now split this over the front and the rear axle. The other thing too is the edit the brake regen map. That is where you can specify your individual brake regen, particularly if you want to play your, if you want to really dial in what you want from the brake regen system. You can also, when you click here to enable regen on the front axle, you can specify what your brake bias is. So let's take a look at what you get back from the ChassisSim EV powertrain, and in particular, the important variables that you get back from the ChassisSim EV powertrain toolbox. So this is an example of a road car range calculation that I did. So what we've got here, the real important things to note is the pack voltage, the current pack, ampere hour pack, and your charge power. The voltage pack will tell you how the voltage will sag through the run. So this is pretty much your danger Will Robinson sign, is if you're probably overworking the pack or you need to go to better cells. The current pack turns you what your current draw is going to be. These spikes here is when you're under. These spikes here is when you're under regen. Your ampere hour pack, that tells you how much you've used for the run. That's a really important variable because it'll tell you what it'll tell you for a particular run. Okay, this is going to be a really important thing to size the battery pack, and this is your charge power. How much charge you're actually being able to get in terms of kilowatts, how you're being able to get back through the regen system, which really sort of segues into an important topic. Where does the ChassisSim EV powertrain toolbox fit into the packing order? Now, part of the problem is that one of the things that you'll deal with from a simulation perspective is that you mentioned EV powertrain simulation, and people want you to define a brushless motor down to the nearest 0.1 of a decimal in terms of a kV. They want you to do it down to the nearest capacitor control strategy of what you need from an electronic speed control. If that's what you're looking for the ChassisSim EV powertrain toolbox, you will be sorely disappointed. However, what the ChassisSim EV powertrain toolbox does do is it allows you to really specify the targets that you want from an electric powertrain toolbox. So you can go over to the EV propulsion guys and say, right, this is how I want my EV, these are basically the targets I want for voltage, charge power, ampere hour packs. if you're specifying, and also too, if you're specifying a brake-by-wire system, what the ChassisSim EV Powertrain toolbox does is it allows you to do the dance between what you want from a regen map to what you want from mechanical balance. So when you're sizing the brake-by-wire, you're actually doing it from a place of knowledge, as opposed to going, oh, well, I suppose this will work. This is where the ChassisSim EV Powertrain toolbox fits into the pecking order. It also allows you to see what you've got to do from a chassis setup perspective, so you can actually free up the amount of regen to be able to put charge back into the battery. So that's pretty much where ChassisSim fits into ChassisSim fits into the pecking order. So to sum up, okay, as we've seen, understanding EVs is not rocket science. It's actually really, really straightforward. You then use ChassisSim to fine-tune your variables, but the key thing is what the ChassisSim EV Powertrain toolbox does is it helps you dial in what to expect from your electric powertrain. That's where it fits into the pecking order. Now, for those of you who are, but you know what? At this point in the game, for those, it's now time. I'm turning it over to you guys. So what you now need to do is that you need to for those of you who are existing members of the ChassisSim community, you've got this tutorial now. So start having a bit of a play with this. And for those of you who are not members of the existing ChassisSim community, download the online simulation, buy a few credits, and give this take this out for a spin. And you can see what a powerful tool the ChassisSim EV Powertrain toolbox is. And we will catch you in the next ChassisSim video tutorial.